Hi participants, I hope you are enjoying the course. Okay, so we are continuing our deep dive into heat exchanger design, heat exchanger network design. In the previous class, we and again just to get started with, again we are using reference number 2 and 3. अब पूरा कट कर दीजिए एक बार. ओके, अभी स्टार्ट कर देता हूँ. स्टार्ट. Hi participants. I hope you are enjoying our journey on computational process design NPTEL course. We will continue our deep dive into heat exchanger network design. So this session is about heat exchanger network design 2, wherein we speak about multiple streams and how to design composite curves, and we speak about a concept called pinch, and we use an idea called problem table algorithm to identify to design the heat exchanger to design the heat exchanger networks. So again, just to recap, so we were using the reference number 2 and 3, which is written by Douglas and Smith respectively, as the textbook or the reference book for this particular part of the course. So just to recap what we were doing in heat exchanger design, which rather heat exchanger network design. In the previous lecture, we spoke about there are 3 modes of heat transfer. If you recall, that this is conduction, convection, and radiation. And we also talk about 3 basic resistance in shell and tube heat exchangers, and we talk about how to compute the overall heat transfer coefficient, how to compute the total heat transferred. Okay, and in connection to basic resistance, there is that is connected to the tube wall, okay, outside the shell and inside the tube side film. Then we spoke about various type of the heat exchanger flows, which is counter flow, parallel flow, or cross flow, and we found that then we spoke about something known as composite curves, as we see over here. We spoke about composite curve, and what we have found that the area of overlap in the composite curve increases, okay, the region and the heat transfer also increases, and it is predominantly determined by the factor what we call it as delta T minimum. And this is all analysis we were doing with the help of a single stream, one hot and one cold stream, and we have drawn the composite curve, and the areas which are not covered by the composite curve, what it is marked by the in the hot side it is marked by the red line, and cold side it is marked by the blue line, has to be supplied as additional utilities for here in on the steam on the upper side. It has to be supplied by a hot utility. It is probably or potentially it would be the steam, and in the cold side it should be supplied by cooling water, just to further reduce the heat. In the other side, you are further supplying the heat. And we talk about delta T minimum, and we can modulate the delta T minimum and thereby bringing the overlap of the composite curves. Thereby controlling the requirement of utility of the cold and utility of the heat. This is what we were studying or we were covering in the last class. So now let's go into a slightly more complicated situation, which is actually very most which actually reflects most in the real time. Okay, so we look for the case where there are more than one streams. Okay, one such case is a process with 2 hot streams and 2 cold streams. So what you could see over here is that, so this is the entire schematic of the process. Okay, so you have a feed that is coming in, feed 1 and feed 2. Okay, feed 1 is passing through a reactor, and of course and goes as feed 2, of course feed 2 coming through the reactor 1 goes as product 2, and feed 1 of course pass through the reactor 1, and is again go to the next reactor, and eventually combines there and goes out as a product. Fine here. So here, so the other part of the stream, you just bring down the temperature. What you could see here, the stream temperature is 250, the other stream, and finally it become 40° C by cooling down, and you kind of strip the uh, gas from the stream, and you get as a product. So this is the simple flow sheet wherein you have multiple streams involved. And why do you say that it is multiple hot stream and multiple cold stream? The feed is of course getting heated here. Okay, so you can see feed 1 and feed 2 are heated from 20 to 180 and 140 to 230 by means of additional heating utilities. And finally, the reactor outputs are cooled down by means of 2 cold utilities. So there are 2 hot streams and 2 cold streams, and eventually you get your desired product. So now our aim is, so rather than providing individual hot streams and cold stream, which is not economical or rather it is energy intensive, can we use the concept of heat recovery to redesign the network so that we can reduce the overall heat utilities, be it cold stream or hot stream. So this would be helpful. So let's look at the structure. So there's a problem, the reactor 1 feed, okay, it's of course is cold, entering at 20° and of course exiting at 180°, and this is of course the delta T and the Cp of the stream, and H you can compute as MCP delta T. Cp here stands for MCP. So what is the difference in terms of the temperature change? When you multiply with the Cp, you will get the delta H. And reactor 1 product, okay, so it is coming one here at 250, okay, and it's of course it get cooled down and eventually goes at 40, okay. So it's of course by the convention delta H is negative here, and Cp is 0.15, which of course we can multiply with Cp 0.15 with the temperature change to get the corresponding delta H. And reactor 2 feed, so it enters here at 140, and of course it's heated by heat utility and become 230 before entering into the reactor 1, and the Cp value is 0.3 which is then get multiplied by the temperature change will give you the delta H. And similarly for the reactor 2 product, which is of course cooling down from 200 to 80° C, which is giving you a negative delta H as per the normal notations and conventions. So now we are going to look the how to, so see we have multiple aims in this part of this exercise. So try to write the composite curves, or rather draw the composite curves. Identify what is known as the pinch point. If you identify the pinch point, okay, so can we use the concept of pinch point to redesign the network so that maximum heat recovery can be obtained, and how to do that systematically. So that's what I think we are going to do in the remaining part of the lecture. So let's look at how do we draw composite curves if there are multiple streams. Okay, so we have done this if you have single streams, individual streams. So now let us look at how can we do it when we have multiple streams. So let's see the case. Okay, so the temperature of the so see we have multiple cases here. So if you go back here, you can see that 250 so if you just go one slide back, okay, so this is 250° which is cooling down to 40°, and 200° which is cooling down to 80°. So you can see 250° cooling down to 40°, and 200° cooling down to 80°. So these are the two composite curves of cold streams, and whatever we have written is their corresponding Cp values. And what we can now write, so these are their this is the H versus T curve for their individual streams. So now we are going to draw the composite curve of these two together. What we can see here, so it starts from here. So from here up till here it is so there is no effect of the second stream, what you can see here, but from here to here this regime you have two streams together. So we will have to join these streams together, and finally the streams, after that this stream is standalone. So what we can see over here is, you can see from 40 to 80° C, you just use this part of the stream which we draw over here. From 80 to 200, there is two streams involved. The combined CP of that is the summation of the individual ones, which is 0.25 plus 0.15, which is 0.4. And you can see that till 200, they all, so it's like they work together. So you can just see that up till 200, they actually go together fine, with of course a different slope because their CPs are different. What you may see, and from 200 to 250, again your the first stream would retain with having a CP of 0.15. You can see that at this point, if you cut down, so this is the heat load, that is delta H value that is needed for the stream up till here. This happen to be 6 megawatt. From here to here, it is going to be 48 megawatt, and from here to here, it is 7.5 megawatt. How are you getting these numbers? Simply by plotting it. So there is no way to analysis further. This is just once you plot and integrate them together, the points of points where it do intersection, you drop a perpendicular down and you find out what are the coordinates, and thereby computing the individual computing the heat utilities of these particular streams. In fact, it's not a heat utility, it is the delta H values. So now coming back to the hot streams. So hot streams there are two hot streams. One is of course going from 20 to 180, the other going from 140 to 230, of course having CP values 0.2 and 0.3. So now we have to integrate them together. So what we could see here, 20 to 140, of course there is only the stream with CP 0.2, we will retain that. And between 140 to 180, there are two streams having different CP. So we have to integrate join them together. So the aggregate CP is a summation of, or rather the composite CP or aggregate CP is a summation of the individual CPs, and we just sum them up as per this equation. And from here, from the last part, your the CP with the stream with point CP remains, and we just draw them together. And when we draw perpendiculars at each of these points, we could find out the H values. So from here to here, it is 32, 20, and eventually 15. So this is the way in which we draw the composite curves of hot and cold streams. So what are we gaining out of this? So this composite curve illustrates the temperature versus heat content for the combined hot and cold streams in the heat exchanger network. And CP values show the heat capacity, flow rate at different segment of this process, and we have seen how do we compute the CP composite. It is just the aggregate or summation of the individual CPs. So once this is done, now the next step is placing the composite stream of hot and composite stream of cold together in a H versus T plot. That is what we have done it here. This is the composite curve arrangement. So the first one that we see here, which is marked by 1, is the composite stream of the hot and the cold placed in the same scale. Okay, and you can see that and so what are the observations here? So see, this composite curves actually converge at certain point and start diverging from here. You can see that this is you can see all the composite curves of the hot, which is of course on the top, and cold, which is on the bottom. So they come to an agreement till certain point and start diverging that. So the point at which they are close to each other, maximally close to each other, where you find out what is the delta T minimum. So everywhere you have the delta T, and the point H where it comes to have the come close is where we have the minimum delta T. So this particular point is called pinch point, and we will see that later little bit more detail how to use this pinch point. Again, so you can get now what we could find out, what we can see that from this point, okay, there is no cold stream effect. So you have to find additional cold utility here as QC min. From here So you will have to find an additional hot utility, and the heat recovery you can get in the middle. So the coverage of this entire plot will be over here, and which you can recover a heat, and the additional utility that you need to supply is 10 from the cold side, 10 megawatt from the cold side, or by means of cooling water or so, and 7.5 from the hot side. And this would of course invariably vary if you change the delta T minimum. So if you change the delta T minimum to 20 degrees C, so we can of course if the delta T minimum is 20 degrees C, you see that the curves would be further separated, and you can see the coverage become less. As a result, you need to have so your Q recovered, the heat that is recovered will also be less. Fine. And which essentially means that the how much ever the remaining part of the recovered heat will have to be transferred as cold utility or hot utility, that would result in the increase in QC min and QH min. So let's look at so this insights we will get by keeping this composite curve together of the cold stream and the hot stream. And what we know that delta T minimum is the closest temperature between this hot and cold stream, and moving the composite curve together, of course horizontally, which essentially mean that you move it down or up. Okay, your delta T can be varied, and QC min and QH min QREC change the delta T change as delta T varies. So your hot utility, cold utility, and of course the total heat recovered will be varied if you change the delta T minimum. And what you can also see some interesting aspect of it. So see, this is how you place the total energy, cost and total. So this line is about energy, this is the cost, and this is the total of all of this. What you can see that when you are at point number 1, okay, you see that so so in this particular case your delta T minimum is small, fine, which essentially mean that you need to have a larger area to cover the to effect that particular heat exchanger design. So as a result, you can see that the overall cost of course seems to be little lesser, but your capital cost sometime will be on the higher side. So when we move the delta T minimum to the point number 2, you see the capital cost will be eventually lesser because your delta T is high and you need to have lesser area to effect this particular temperature, but overall cost will be typically on the higher side. Why? Because you are adding, you are separately supplying hot utilities and cold utilities. So of course there is a trade-off. The idea here is that you need to identify that there is a trade-off between having a smaller delta T minimum and higher delta T minimum, and further there is certain physically achievable delta T min. So what you can see here is that small delta T minimum requires pure counter current flow. Pure counter current flow typically not possible to achieve by shell and tube heat exchangers. Why? Because you would have baffles there, and there are other obstructions if you put. So 100% counter current flow may not be achieved by shell and tube heat exchangers. So a delta T of 5 degree C, which is of course lesser than typically recommended here. Of course 10 degree C is what we are showing here. If you want further lower, we need to go for plate heat exchangers. And if you wanted to further down the delta T min, so which is like 1 to 2 degree C, this can only be achieved by plate fin heat exchangers. And in terms of considering the operational practicalities, okay, typically we limit the delta T min to 5 degree C, and anything below 5 degree C is ill advised. So it's not very easy to realize in practice. So under any special circumstances prevail, then only we will go for a delta T min, which essentially mean that the pinch point is so these curves are pretty much close to each other. Uh, when you have the delta T minimum less than 5, which is typically not recommended considering the operational difficulties and the cost involved. So, let us go one step forward and speak little bit more about the pinch. So, before that, let us understand what is a heat source and a heat sink. So, you can see this is the same delta T H versus T plot of cold stream and hot stream placed each other, and the lower part we can see that you will have to have certain so you will have to provide utilities in the cold side as well as the hot side whenever the curves are not covering each other. Okay. So, what is a heat source? Heat source is a heat recovery system yeah, or a set of process streams that is needed to release heat, and heat sink, of course, as we saw here, is conversely is a process stream or a set of process streams that need to absorb heat. The hot composite stream below the pinch point. So, pinch point is where when you see the delta T minimum. The hot composite stream below the pinch point can transfer to cold composite curve at the above pinch point. So, if you look at this curve here, okay. So, if you wanted to transfer heat between the streams, because the ideal aim of heat recovery is the transferring of heat between a causal stream. Okay. So, if you are below the pinch point, the hot composite, so what is possible? So, you can see that we can always transfer heat from a hot stream to cold stream. So, if you are above the pinch point, that is fairly possible. This is the pinch, and you can very nicely transfer heat from a hot um, stream to a cold stream, which is of course not possible if you are below the pinch point. The hot composite stream below the pinch point cannot transfer heat to a cold stream above the pinch point. So this the cold stream, your hot stream is here below the pinch point, hot stream is above the pinch point. So this particular arrangement is not possible. And but the other way around is always possible. The hot composite stream above the pinch point can transfer the heat to cold composite curve below the point. So this kind of insight we will be able to derive when we draw this composite curves of cold streams and heat streams together. Okay. So, let us say if you are adding an additional heat of xp, so you above the heat utility. So, if the curves are not covering each other, the remaining part of the heat, be it for cold or being from the hot side, has to be managed by some type of heat utility. So, which essentially means if any stream above the coverage of the above the pinch point, if they are not the above coverage has to be transferred by a hot utility. Here it is cold utility. Let us say we are adding additional heat above that into the hot utility. So, this heat has to be will be transferred through the hot stream to the cold stream and finally get extracted via the cold stream. So, there are ways in which if you just supply it, we can also extract it over here by means of operations known as heat pumps. Okay. And or you could transfer it throughout and get it in the cold stream. And if you see if let us say if you are providing the heat not in the hot stream, but the cold stream, so it would eventually come back in the cold stream. So these kind of additional heat addition typically not recommended. Why? Because especially when you add heat in the cold stream, it would typically increase the heat of the cold stream and eventually heat transfer become more constrained. Okay. So this is so a proper arrangement would require just not addition of heat, just not the removal of heat arbitrarily, but following the correct principles of heat recovery. So let us look at the case. There are certain threshold problems. We shall continue. There are certain threshold problems wherein you see that the coverage we can attribute by moving the hot stream and cold stream. So look at the case one, wherein you need to supply hot utility here and cold utility here. By moving the composite curve, what we can achieve here is that, so this is the regime of this. So, you need to supply certain QC min and H min, QH min. So, if you move these curves parallel to each other, what we can see that the delta mean of course changes. The delta mean would reduce, and it would reach as a delta t, delta h, delta t threshold. And in this point, so this is a case of one particular threshold where we see that you don't require any additional hot utility here. The hot side has been the hots the requirement of the hot utility has been adjusted by moving them together. So there is the coverage is complete at the hot side, but you can see that there is certain there is certain void in the cold stream. So anything, and you can further move it back. So when you further move it down, you can see that you need to extract heat from either side, from the either side of the you need to cool down the stream on either side. So again, what we can see here is that when it reaches the delta T threshold, okay, which is of course at this point, even if you move it further, your there is no further change in terms of the uh, heat that is being required. Your QH min would stand to be 0. Your QC min in these two conditions would be the summation of the QC min in this at this point plus at this point. So what are we trying to say? So your delta T threshold is the delta T min when either QC min or QH min is 0. So here we can see that the QH min is 0. You have moved the curve in such a way that the overlap is complete at the hot side. So your delta H threshold can be equal to delta T optimum. So let's see, we will just go there before that. So what we can see that, so there is no pinch occurs at the threshold problem. So pinch point requires the transfer of heat from either side. So either from cold utility to hot utility and hot utility to cold utility. When you are at the threshold condition, the pinch never exists, but addition of multiple utilities, if you add more utilities into the system, you can regain the pinch. Okay. So, and in the threshold problems, one of the utility requirement may disappear. Here, as we also see, the hot utility requirement has been completely disappeared here. So, in this case also, we are only supplying cold utility. So, and once you are below once you are after the threshold, when you further move the curve backwards, the total cold utility will not be reduced as in here. So it comes to a threshold, and the summation, so whatever cold utility here in whatever we are seeing at the threshold will still remain. When you further move it backwards, it will be the sum of the cold utility at this point and this point. Now coming back, how do we see this? So see, so this is the total energy and capital energy. So capital investment and total energy cost and total cost, and as a function of cost versus delta T minimum. So what you can see here, the optimum occurs somewhere here at near the threshold or above. So that's what it is written here. The no so delta T threshold can be equal to delta T optima, or it can be it can be on the right side as well, but it never goes back, which essentially means that your optima will not be any time below the threshold. Your threshold can be below the optima, but optima will not be below the threshold. So here you can see that at the threshold your energy requirement become flat. So you can see over here. So, and finally you might see that, and your optima is still over here, but your threshold is going to be maybe lesser than that. So these are certain conditions that you might see while playing around with the hot stream and cold stream, and this is how. So if you are reaching a threshold problem, the advantage is that one of the utilities requirement you can make it disappear. But further moving around the streams will not reduce the requirement of the utilities. It would be what, so at the threshold you see that, so in this particular the case, the heat utility, hot utility has become completely uh, not required below the threshold, but your cold utility will remain the same. So even if you further reduce it back, the resultant cold utility at either ends would be the summation of the QC min at the delta T threshold. So how to, so see, whatever we have done till now is all about uh, keeping or rather arranging the drawings and inferring the details from them. So it's basically you were using graphics or visual to do that. So so in many cases we may not be able to draw the visuals. So for instance, all the inferences what we have done here is by drawing the composite curves. So the composite curves, uh, drawing itself is a complicated procedure or maybe a painful affair. So the what we are going to do here is, can we do or can we achieve the same, okay, by means of certain numerical methods. So one such algorithm or one such procedure that helps you to identify the pinch points and also identifying which stream to which stream you need to transfer the heat. So these kind of informations, of course you can get it from the composite curve if it is drawn. Can we do it by means of algorithmically? So the problem table algorithm is one such way to achieve that. So to achieve that, what you have to do, okay, so this is you have the the data available. So what we are trying to do is we are trying to develop draw the intervals or make the intervals between the composite plots. So at certain point one problem arises. What is the problem? So when we try to draw, when we try to divide the composite curves into intervals, so you can see over here, the delta mean is coming here. So no way that you can draw a line horizontally to get the effect of the delta T mean. So at least you should get the delta T mean, which is of course the pinch point for the further analysis. So as a result, so that's what it is written. So when we are making the interval, sometimes temperature driving forces are not feasible to obtain. So what we can do in those contexts? So shifting the composite curves. So you can move the composite curves closer so that they tend to touch. So when they touches, okay, you can draw a line, and when you make the interval exactly, you may be able to capture the pinpoint. Shifting the composite curves in temperature allows complete heat recovery within the temperature intervals. So see, please mind that this is not this is just a coordinate transformation and has no bearing in terms of the results that we get. So why we are saying this? Because see, when even if you make this composite curves to come together, the overall coverage is still remain the same. You are only making it to we are only making them come to close or come far. So we are not trying to see, we are not trying to make them away from the uh, coordinate of delta t, but we are trying to keep them together, trying to bring them together. So the entire coverage of the shifted composite curve would be the same as that of the individual composite curve. So the analysis results will still hold. So once we do that, when we do that, we can see that we will be able to extract the point of delta t min as a single point, because the composite curve will now touch each other. So this is typically done. How do we do it? So this is typically done by shifting the temperature obtained by subtracting the delta T min by 2 from the hot streams and adding delta T min by 2 to the cold stream. So how to do that? Let's see. So we have the cold streams which has 20 what you call inlet at 20 degrees C, exit at 25 degrees C. So delta T min is 10 degrees. So you add 5 to Ts, so that become 25, and 180 to become 185. Of course, I have just noted down the corresponding Cp values. Okay, and for the hot streams, So delta T min by 2 we have to subtract. So 250 become 245, 40 become 35, and the same here. So here the so it's cold stream, we have to add up. So 140 become 145, 230 become 235, and hot stream 200 become 195, and 80 become 75. And as a result, see, you are now trying to bring this curve close together and eventually touch at the point of the pinch. So there is we'll be able, when we divide the intervals, we'll be able to exactly capture the pinch point, which is not possible in this case, because when we draw at this point, so as long as we don't get this on a straight line or a horizontal line, we will not be able to capture the pinch point in the when we divide, or rather segment the composite curve horizontally. So now what is the next step in the problem table algorithm? So we see that, so now we have to make a table, of course, and the table should contain all the temperatures of the shifted coordinate. So it should contain 25, it should contain 35, it should contain 75, and others. So let's go back and see that. So you have here 25, 35, 75, 145, 185, 195, 235, and 245. So this is the temperature. These are the temperature that you will capture in the problem table. And let's mark the streams. Okay, your cold stream is of course now entering at 25 and exiting at 185, which is CP of 0.2, and one other hot stream enters at 245 and exiting at 35, and another cold stream enters at 145 and exiting at 235, and the last hot stream enters at 195 and exits at 75. So we are just marking it. So the cold streams are drawn by blue lines and hot streams are drawn by red lines, and so whatever we have drawn there has been captured by means of the sequences. So the stream 1 is a cold stream, it enters as 25 and exits at 185. Stream number 2 is of course a hot stream, enters at 245 and exits at 35, and the remaining others. And now we are going to draw the delta T differences. So between 235 to 245 it is 10 degree, 195 to 235 it is 40, and 185 to 190 it is 10, and you make the entire delta T differences between each of these steps. So next is computing the delta CP differences. So how do we compute it? So just look at here. So the CP here is CP cold, summation of the CP cold minus summation of the CP hot. So but in this particular interval, you can see it is only the hot stream with a CP of 0.5. So there is no cold stream here. 0 minus 0.15, you will get 0 minus 0.15. Okay. And when we come to the next interval, so of course there is a cold stream and a hot stream. The CP value of the cold stream is 0.3 and CP value of the hot stream is 0.15. So difference between 0.3 and 0.15 is plus 0.15. So by this way you populate the entire CP values. For instance, if you come back here in the last row, only one cold stream having CP value of 0.2. If you so let's say take an intermediate place wherein you have three streams. Okay, so two hot streams having CP values 0.25 and 0.15 summed up to 0.4, and CP value of the cold stream here is at 0.2. So 0.2 minus 0.4 would be minus 0.2. So this is how you develop the CP differences or delta CP, and multiplying the delta T versus the CP give you the delta H internal. And you can see that 10 times minus 0.15 would be 1.5, and for instance 10 times minus 0.1 is minus 1, and you kind of develop this particular column. And last, of course, 10 times 0.2 is 2, and you can see there are signs here. So negative signs indicates that it is a surplus and positive signs indicate that it is a deficit. So what we can see that, so in the first temperature interval there is a surplus surplus heat, and the second temperature interval it is a deficit and surplus, deficit, and so on and so forth. So now, so once we identify the surplus and deficit in each of this interval, now how do we how do we can make this uh, feasible? So that's what the next thing. So how to transfer the surplus to the deficit, and how to fulfill the deficit if even if you are supplying surplus and still there are deficit, how do we do that? So this is what would be the next step in the problem table algorithm. So what we can see here, so again, so this is a sequence table of a problem table cascade. So this is again the same temperatures that we have changed from 25 to 45. And you can see you at the beyond the composite curve, either you may have a hot utility, and below the cold side of the composite curve you have the cold utility. Fine. So let's assume that we don't have any more hot utility, and whatever delta H that we have gotten is what we have reported over here. So this minus plus 6 minus 0.1 4 up till 2 is what is being presented over here. So now let's start transferring the heat. Okay. So 0 minus 0.15 become the requirement here is 1.5. Okay. 1.5 minus 6 become minus 4.5, and when you keep on doing all of this, it will be eventually this would be the number that you are going to get. And you may see that so the maximum utility that you might require here is minus 7.5. Okay, so now what we need to do is you have to make that to 0. So by adding a additional heat utility. Fine. The heat utility that we need here is 7.5. So minus 7.5 to make it 0, you need to add a heat utility of plus 7.5. So when you add that plus 7.5 as a heat utility, what you could see that, so minus 1.5, this become 9, this become so see 7.5 minus 1.59, 9 minus 6 become 3. Okay, 3 minus 1 become 4, and so on and so forth. And you have anyway you have a cold utility requirement of 25 megawatt, that would be added to 7.5 become 32.5 megawatt. So what are we doing here? Just to summarize, so this is how we design the segmented the what you call how do we design the heat transfer requirement in each segments. In the cascade, surplus heat from transferred from high to low temperature, and of course the remaining. So to make the maximum what you call the maximum here is minus 7.5 is the deficit, and you can add that by supplying a heat utility value of 7.5, and the whole becomes 0. So once that is done, okay, so see what have we done? We have added additional heat utility and additional cold utility. So next is selecting the utility. So how to select the utility? So this is the typical T versus H curve, and you need to add heat utility, hot utility here, and cold utility here. And in this curve, whatever we have given as the shaded area are the pockets of heat recovery, and where in which we can recover the heat within the process before the external utilities are required. So this is where we could just do internal recovery by means of by means of integration, and beyond that, of course, you have to add the utility. This part remains the utility, and here this part remains the cold utility. And how can you do this? So the hot utility can be typically an LP steam like this, or even a hot oil like this, and typically cold utility will be mostly a cooling water stream. So so once you have to decide upon what is the utility to be selected, then now we can So now we can just see, can we do some more possibility of integration by means of uh, by adding a heat engine or removing the or by integrating a heat pump. This opportunity eventually result in cogeneration, which essentially you say that you can also add a steam turbine or a gas turbine to the system. So you can try adding a heat engine in the across the pinch point. So there are two ways to add an heat engine into the pinpoint. Anyway, we need to add an additional QH min as a heat utility, and we say that we are just not adding QH min, but we are adding a summation of QH min plus QHE. And you can, what's the advantage here? Heat engine uses some of this energy, and of course you can produce useful work, okay, and the remaining would be transferred back. And what is the sequence in which you can put the heat engine? So one way to put the heat engine across the pinch, which essentially means that it takes the heat of the QHE from the hot utility. Of course, it produces useful work here, which may be used for anything else, maybe for power generation and so on and so forth. The remaining heat would be rejected back to the streams below pinch. So this is definitely not recommended, because this is, so you see that there is heat that is being supplied below pinch, which essentially means that we are trying to heat the cold stream that would actually hamper the heat recovery from the hot stream in a natural fashion. But when we integrate the heat engine in the above pinch, which essentially means that it takes out the QHE, it gives the work and send the heat back to the heat back above the pinch, which is QHE minus W. So as a result, what would happen? So this additional heat is applied. This additional heat is obtained uh, in the top part above pinch. So you only need to supply less heat from the utility. So this, as we are receiving this QHE minus W as an additional heat into the above pinch, so the total heat requirement from the utility is also reduced by QHE minus W. So and we are also getting the useful work. So this is one way to integrate heat engine into the one way to extract useful work and integrate heat engine into the system. So this is how you do cogeneration in the so for instance, by means of turbine and by means of steam generator uh, or gas turbine into the plant. So you can also put a heat pump wherein we extract the we extract QHP from the below pinch, and you, of course, you need to supply work to make the heat pump work. As a result, what would happen? You can send in QHP plus W as an additional heat to the uh, above pinch, which would again reduces the hot utilities requirement here. So the key thing to be looked into here is that when we integrate a heat engine, we never do a cross pinch. We will only do above pinch. Okay, while when we do a heat pump integration, we always do across the pinch. Why? Because let's consider a case we only keep the heat pump above pinch. So what are we doing? It is taking QHP from here. It is, and you take the you again supply W and you supply QHP plus W back. So what is the net gain? Net gain is only W, which is anyway you are supplying over here. So this is definitely not useful. So this is one way to integrate heat pump and heat engine, which essentially result in cogeneration. So what is a heat pump? Just to summarize, it's a device that transfers heat from a heat source to heat sink, usually consuming the work. Heat pumps are used to increase energy efficiency by transferring the heat from a low temperature source to high temperature sink, which would be otherwise wasted. Heat pump can effectively increase the temperature of the heat source, making it suitable for the process that require high temperatures than source providing naturally. In the similar way, when we put a heat engine, what are we doing? Heat engine, after producing useful work, the remaining heat is rejected, which is of course can be result in different operational strategies. So now coming to the last part of this, once we all done is we can actually complete the pinch design. So the so some 2-3 points that to be looked into in the pinch design are the following. At the pinch, the match starts when the when the temperature difference is equal to delta T min, and moving away from the pinch, the temperature must increase. So we will see these 2 points. A feasible match involve linking the hot stream with a cold stream that has larger Cp when you are at above pinch. A feasible match would involve linking a cold stream with a hot stream as a larger Cp when it is below the pinch, and hot utility must not be used below pinch, which means the cold streams must be heated to the pinch temperature by heat recovery. A cold utility can be used if necessary on the hot streams below the pinch, and of course, we need to use an idea called tick-off heuristic. So, if you have a pinch, if you can identify the pinch, the analysis now split into two, something that is above pinch or something that is below pinch. So, now let us see how this is done. Okay. So, let us look at the same network. So, we have hot stream and cold stream, again it is marked. We will only do, so this is above pinch, which essentially means that CPC is greater than CPH. We will only connect the links between that has a hot stream to a cold stream that is high Cp. So, 0.25, this stream 4 has a Cp of 0.25. So, it should not be connected to the cold stream with uh, having a Cp less than that, which is 0.2. The correct connection would be from stream 4, which has 0.25, it should be higher than that. So, the stream 3 has a Cp of 0.3, which is higher than 0.2. So, you may be able to connect. So, if you connect otherwise, this would result in an infeasible operation. This is the way we can result in feasible operation. Now, how to do it below pinch? Okay, so if you are connecting it below pinch, again, so your cold stream is at 0.2, you cannot connect that to 0.15. So, you can because the Cp value of stream 2 is 0.15 and stream value of cold stream 1 is 0.2. So, the connection should be given to a stream that has higher Cp than 0.2. So, the feasible connection here is between stream 1 and stream 4. So, you can see this is a correct connection. So, the other connection would result in an infeasible operation. So, now the last part, how to we select, in what is the sequence in which we select sequence in which we connect the hot stream and cold stream. So, this is the overall requirement which I have placed here. Stream 1 has a requirement of 8 megawatt, stream 2 has a requirement of 15 megawatt, stream 3 has a requirement of 27 megawatt, and stream 4 has a requirement of 12.5 megawatt. So, now let us start. So, we look for the stream that has the lowest hot stream, that having the lowest power requirement, of course stream 4. So, take the stream 4 here, you can stream 4 and you may be able to connect it with stream 3, okay, so which essentially mean that the stream 4 has been completely utilized. Then take the remaining stream 2, and stream 2 you can connect it to the stream 1 and utilize the 8 megawatt. So, which essentially means the stream 1 is also fully operational. So, that is why we tick them in the sequence, but the stream 3, the remaining part of the stream 2 can be connected to stream 3. So, so it is 15. So, if you take out the 8 out of it, it would be 7, but the stream 3 require 27 megawatt. So, 12.5 plus 7 can only give 19.5. So, you need to put additional 7.5 by means of a hot stream. In the similar way, so this is the sequence in which we operate. In the similar way, when we do an analysis below pinch, there are 3 streams, stream 1 which is having a 24 megawatt requirement, stream 2 which is having a 16.5 megawatt, and stream 4 having 17.5 megawatt. So, the smallest, we take the smallest power required stream, which is stream 2 here, and take out the stream 2 and supply it to stream 1, which would be 16.1 megawatt. As a result, stream 2 is checked out, and you take the stream 4 now, and from stream 4 so yeah, so from the stream 4 you supply the remaining, okay, and what is that is now remaining would be again supplied by so you can see that if you supply 7.5 to the stream 1, Okay, your stream 4, stream 2 would have again 10 megawatt left, and that would be used by means of a cooler by means of cooling water. So this is the sequence in which we connect and above below the pinch. So once you have the analysis of above pinch and below pinch, we could just integrate them together. You place the below pinch connections and above pinch connections together, and you can just integrate them together and mark them back into the original heat exchanger network. So this is how we design the entire heat exchanger network. Okay, so just to summarize our study, so so the curves that represent aggregated heat demand and heat supply within the process are categorized as hot and cold streams. The area of overlap of the composite curves represent the potential for heat recovery, while the extent to which the curves do not overlap indicate the minimum requirement of external heating. The temperature interval heat balance involves the breaking down the process into intervals and analyzing the heat balance in each interval. This allows more granular understanding of the heat transfer within the system and aids in optimizing the heat exchanger design. Pinch analysis is a crucial part of heat exchanger design network. The pinch point represents a critical temperature point in the system where the smallest temperature difference between the hot and cold stream occurs. The point is vital for understanding the limitations of heat recovery uh, and setting realistic energy targets. So, and we have seen threshold problems where either of the hot or cold utility requirement disappears, and the location of the pinch point divides the process into two parts, each with its own energy balance constraints, emphasizing that no heat should be transferred across the pinch to avoid inefficiencies. The problem table methodology what we have learned here is a methodology that helps in calculating the energy targets without relying on the graphical constructions. The algorithm simplifies the process, setting up by temperature intervals and calculating the heat balances, facilitating the design of more efficient heat exchanger networks. The below pinch and above pinch condition has to be met, the CP conditions basically while the design. And lastly, we have to use tick-off heuristics that minimizes the requirement of overall number of heat exchanger unit by utilizing the maximum possible heat transfer between the paired fluids. And stream may be split into multiple parts to alter the CP value to facilitate the heat transfer. So this are the summaries that we have learned today, and I hope by this 2 sessions you were able to learn and understand how heat exchanger designs can be done systematically by utilizing the principles of heat integration and pinch analysis. And the next session would include possibly speaking about how to the geometric design of reactors, and we will further move on to operability and reliability analysis, followed by sustainable process design. And thank you for patiently listening to me, and see you in the next session. Thank you.